Okay, so today we're going to derive the Kelly Criterion for optimal betting. So the Kelly Criterion is the optimal bet size in order to maximize winnings on a game of bets with an unequal payout, meaning we have some odds. So first I'll just state the formula. This is what we're going to show. So the optimal bet percentage, this is going to be a percentage of your overall bankroll, is going to be PW minus 1 minus P over W. So F, that's what we want. This is the optimal ratio of your bankroll to bet. P, this is the probability of winning each bet. And then W is your odds. So this is the win payout to lose payout ratio. Meaning this is the multiplier for your bet. So if you bet $1 and you've got 3-to-1 odds, every time you win, you're going to win $3 instead of 1. But if you lose, you just lose 1. Okay, so the way this is going to work is you're going to start with some initial bankroll. That's however much money you have to work with. Call that X naught. So X is your bankroll, 0 is times 0, the initial bankroll. And then we're going to say that your bankroll after N bets, so we're going to define N in a second. N is going to be the number of bets. We will express this as the nth gain times the initial bankroll. So this is an indexed term. N is the number of bets that have been played out so far. So it's the number of times you've played this game of chance. And so this number is going to change. Every time you bet another time, you're going to get another outcome, and this is going to change the what we'll call gain, modifying your initial bankroll. So this GN, we'll call it the nth gain, is cleverly indexed with a superscript instead of a subscript, because we're actually going to take the nth root to get G. So the nth root of your nth gain, that's just equal to G. So G, this is actually the geometric mean. Geometric mean of all of your gains. So So each time you win or lose a bet, you modify your overall bankroll at that time by multiplying it by some factor. And so if you multiply all of those factors together, that gives you the nth result. The end result, right? So if we spread that out across all n of the bets by taking the nth root of your overall gain that you ended up with, which is the gn, if we take the nth root, that's going to be a value that represents what would happen if we got the same outcome every time. So if we got the same outcome every time, and that was repeated n times, that would lead to our overall gain that we actually have. So G is representative of our overall gain. So now that we've expressed our variables here, let's start to break them down to what they actually are. So our nth gain is, so actually this is going to be the expected value, because we don't actually know what the result is. So all we can do is predict what we expect the value of our bankroll to be. So the expected value of our gain is going to be, so every time we win, we're going to increase our bankroll by a factor of how much we've bet times the odds. And that's going to occur with probability P times the number of bets so far, and, sorry, not plus, but times the number of times, the amount of loss we've made. So every time we lose our bet F. We subtract that from the whole. And that's going to occur with probability 1 minus P. It's the remaining probability times the number of bets N. So this is going to be the expected outcome, the expected gain after N bets. So let's say it's let's say that the odds are not the odds, but the probability of winning is 50. So we have 50-50. Then we're going to have half of N times this factor of 1 plus FW. So 1 plus FW is raised to 1/2 of N, that power. And then the other half of N, that's 1 minus F, is raised to that power. Okay, so then, since we're taking the nth root, well, then the N just goes away. And so our representative gain, or our geometric mean, is going to be based just on the initial, well, the bet size that we make, which is F, which we're trying to optimize, the odds, and the probability of winning. So, in order to maximize this expected gain, we need to take the derivative with respect to F, because that's what we can change in order to optimize this. So assume the odds are given and the probability is some fixed number. So let's take the derivative. So using the product rule, the derivative of the first term is P times 1 plus FW to the P minus 1, but then this is a function within the parentheses, so we need to multiply it by its derivative. That's the chain rule. And remember, that's with respect to F, so it's the constant W. And then we leave the other term alone. And then for the next term, we leave the first term alone. And then we have the derivative of the second expression, which is 1 minus P times 1 minus F to the 1 minus P minus 1. And again, by the chain rule, we have a factor of -1. And so in order to optimize this, this should by definition equal 0. And so let's simplify this a bit. So we have P 1 plus FW, P minus 1, W 1 minus F to the 1 minus P. And since we have this negative here, I'm just going to move everything to the other side. So 1 plus FW to the P times 1 minus P times 1 minus F to the 1 minus P minus 1. Okay, so now let's see what we can cancel. So, so we have this 1 plus FW to the P. That part can cancel out. Meaning we know this term's never 0, so it's okay. We can divide both sides by that because it's not 0. This number should never be 0. First of all, because f should be positive, we should not allow. Well, you can't place a negative bet anyways, and then odds would obviously be positive. Otherwise, there would be no reason to play this game. Okay, so we've canceled that, and then we also have 1 minus f to the 1 minus p power. So that much can cancel out. And again, that is non-zero because the only way for that to be 0 is if f equals 1, and that means you bet your entire bankroll. So that is technically allowed here, but that would be the limit condition. So basically the largest bet we can make is going to be our entire bankroll. So we're going to make an assumption that f does not equal 0, does not equal 1, although it can still equal that. So it still might equal that here. And so we're going to keep solving that and still allow that as a possibility, but that will be a limit condition. So basically we're assuming f can be as close as possible to 1 without equaling 1 here. Okay. So now, we need to solve for f. That's what we're trying to solve here. So let us combine all of the f terms together. So PW, I'm going to move the 1 minus P over to the left side. And on the right side, I'm going to move the 1 plus FW. So I multiplied both sides by 1 plus FW. And then we have 1 minus F to the negative 1 remaining, so that's on the bottom. Okay, and now we can cross multiply. And now let's distribute. Okay, so now we see that we have minus PWF on both sides. We can cancel that. And so all we have is one term with F. So we'll isolate that term. So we have PW minus 1 minus P, leaving it in that form because we can see that the formula now jumps right out at us. And we could also, instead of writing 1 minus P, we leave it like that because 1 minus P represents the probability of losing, which we could instead write as Q if we like. Q is probability of losing a bet. Okay. So how do we know that's actually a maximum and not a minimum? Well, if we go up here, the derivative is positive when f is less than that, negative when f is greater than that. So we need to make sure that we're at a peak and not a valley. Okay, so we just need to check where this is actually greater than 0. We want to verify that f being less than that optimal number is going to ensure this number is greater than 0, and that will mean it's a maximum. So what we need is this to be greater than or equal to that. Okay, so when we canceled this 1 minus f to the 1 minus p, those are positive numbers, so we didn't change the inequality. And then we didn't flip the expression here. When we multiplied some terms over here, all of these were positive numbers, so we still haven't changed the direction of the inequality. Okay, so just tracking that inequality. When we cross multiplied, again we're dealing with only positive numbers, so we haven't flipped the inequality. Okay, we're just distributing here, we still haven't changed anything. And so here's where it flips. So now we're solving for FW, so now it's on the left instead of the right. So FW less than or equal to that. This is where it's going to be positive. The derivative is going to be positive. And then if we just reverse that inequality, so what we're doing here is making sure that's positive. But if we just reverse that inequality here, well, that's going to reverse it all the way down the line. So that's going to be now greater than or equal to, and so that would correspond to the negative derivative in that case. And so basically we've shown that this is indeed the maximizer of our expected gain, and therefore it is the optimal bet size. So this is applicable for any betting game where you can guarantee a probability of winning each time and for some fixed odds. So f is going to be given as a ratio. So let's say you get f equals 0.5. That means you're going to bet half of your bankroll. So this might be good for blackjack and other casino games, but not necessarily for trading, because trading is not really a truly random process, and so you have to be careful with that because you can't really guarantee the probabilities or the odds you get, which might be risk-reward ratio. So anyways, this is the optimal bet size, given that you are able to guarantee all of these variables here are fixed numbers. Alright, thank you, and let me know what else you'd like me to prove.